Okay, so we are extremely happy to have Chong Wang from Perimeter to give us a very special talk. It is a little bit outside of the kind of talks we usually have, but then this is also a seminar channel on quantum field theory, and we got interested in this topic because of Yassir's colloquium on quantum spin liquids, where he was
I
talking
see.
about this marvelous results of Dirac spin liquids, especially obtained by you. And so we thought that we should have you here, and we are so lucky that you have agreed to give a talk on our channel. So okay, we are now over to you then to deliver the talk today.
Okay, thanks, and yeah, thanks for the invitation. And also during my talk, please feel free to interrupt and ask me to clarify basics, right? Because the story I want to tell you today is about monopoles in essentially three-dimensional quantum electrodynamics. Three because I will mostly working 2+1 dimension. And here are my collaborators. Xueyang Song, who's a student at Harvard. Yinchen He is my colleague at Perimeter, and Ashwin is from, I assume many of you know him. So here are the references, and if I have time toward the end, I'll also be briefly mentioning some of the more recent developments, but the basic stuff are here in these two papers. Okay. So this is a program that we're quite excited over the past several years. So this is what the roughly what the program looks like. Apparently, several on face value different topics in condensed matter physics, also in quantum field theory, got put together through the study of an object called monopoles or instantons in QED3. So the topic is related to what's called the U1 Dirac spin liquid in two-dimensional frustrated quantum magnetism. And there, the instantons and monopoles actually, as I will show you, actually comes with consequences that are measurable in experiments and numerics. They're also related to various symmetry breaking competing orders. If I go out of the critical U1 Dirac spin liquid regime, things like antiferromagnets or what's called the valence bond solids. So basically various types of magnets. So this topic has been there for a while. Since in condensed matter physics, people have been thinking about them since at least late 80s or early 90s. But there are some subtle aspects that never get quite clarified. So the recent realization is that to really understand those subtleties, it turns out what you need, the tool you need, is really comes from another corner in modern condensed matter physics. That's the corner of band topology, or if you prefer, sometimes called the symmetry protected topological phases. Notions like topological insulator or one-near center and polarizations, surprisingly, they enter into the story and helps us to understand some subtle aspects of monopoles on lattice QED3. Okay. So that's the story I'll be telling you today. But before that, let me put everyone on the same page. Let me give a brief introduction to the subject of U1 Dirac spin liquids. So this is a fun subject, both from a purely field theoretical point of view, as well as from condensed matter physics. And if you're not familiar with this subject, here are the two kind of standard references. Both are quite pedagogical. Okay. So let me begin. So the kind of system ultimately that I'll be interested in are two-dimensional frustrated quantum magnetic systems. So it's a lattice spin system basically. So let's imagine, say, a triangle lattice. It doesn't have to be triangle, but just for concreteness, let me work on the triangle lattice, and it will turn out to be the most interesting one anyway. So on each lattice side, let me put a spin moment, and let's just say spin half moment per side, right? So the Hamiltonian I'll write it in this form. So this one is the usual Heisenberg antiferromagnetic coupling, and ... represent possibly higher order or further neighbor couplings. So I'm not going to specify exactly what it looks like. Okay. So the idea is to ask what are the phases that are probably interesting out there if I explore the parameter space, right? So if I, take, include ... like second neighbor or funny couplings, right? So what are the possible phases? So there's the ancient or rather classic approach using what's called the mean field decomposition. The idea is simple. You basically consider a magnetically ordered state where you can basically replace one of the spin operators by its expectation values, right? And then you solve the theory consistently. Right? That's been successful, at least qualitatively, for the usual type of ferromagnets or antiferromagnets. Okay? For example, if I have this type of what's called the 120 order, where the spins order in this way, right? They form some spiral and they rotate by 120 degree every time you move to a nearby lattice site. You can describe it this way quite successfully, right? Of course, you don't stop at the mean field. You can include small fluctuation. That's how you get things like Goldstone modes and so on. Okay? So that's a pretty nice approach. The problem is that if I want to describe more exotic quantum phases, especially quantum phases with some intrinsic non-trivial degree of quantum entanglements, of many-body quantum entanglements, this approach doesn't quite do that. Right? So it misses some interesting phase. But we still like the idea of mean field, right? Because it converts a hopelessly complicated problem into something that we know how to do, right? Essentially it converts into some trivial problem. And after all, human beings only understand trivial stuff. So over the past several decades, I think people figured out that a nice trick to circumvent the problem with the usual mean field theory is to do mean field theory in a funny basis, right? Not in the original physical basis. Rather, you consider fictitious objects, called partons, so these are basically fictitious or auxiliary particles in this particular case. And let me do fermions. So the idea is to rewrite a spin operator in this way, where this F, so this index I is the lattice site, so it's a real space position. And this F operator is a spin half fermion operator. Right? So this S is just an ordinary spin 1/2 angular momentum, right? But this F and the S operator transforms as vectors under the spin SO3 symmetry, the standard story. But when I do this kind of decomposition, each F fermion transforms as a spinor or spin half representation under the spin SO3. So it's a fraction of it carries a fractional quantum number under the SO3 or projective representation, if you like. Okay. And sigma is the Pauli matrix. So if I write this, if I rewrite the spin operator this way, I essentially convert the problem into the system of a spin Hamiltonian into a problem of strongly interacting fermions. Right? It's in fact hopelessly strongly interacting, because if you literally substitute this expression into the original Hamiltonian, it looks way too complicated to be solvable. However, in this basis, at least, you can talk about some kind of mean field approximation or mean field ansatz, right? You basically just, instead of solving the full problem in the spirit of the usual mean field theory, you basically instead solve an ansatz, which is just a free fermion problem. Right? So it's, instead of a hopelessly complicated problem, you just solve the simplest possible problem in many-body physics. Okay. So that's called the parton trick. Of course, as in ordinary mean field theory, you don't stop there. You should, on top of that, include at least some weak fluctuation and see what's going what happens.
So Chong, what exactly is the mean field here? Is it Tij, this object?
Yes,
or?
yes. Okay, let me specify. So so here, when I say mean field ansatz, so I'm suppressing, I'm assuming spin SO3 rotation symmetry, so I'm suppressing the spin index alpha. And Tij is a parameter which will eventually be a number for a particular mean field ansatz. But Tij obviously has there are some choices for Tij, and the idea is there exists some choice that are good.
Yeah, then a very nice question. So you now have basically 4 degrees of freedom, right? Once you from the original 3 degrees of freedom per site.
Yes, yes. I'll come back to that. That's an important point. That's an absolutely crucial point. Yeah, but if you do the zeroth order thing, if you're very naive, then you just replace it by a free fermion Hamiltonian with some choice of the this Tij, which we call hopping parameter. Oh, okay. Before I go to that Hilbert space thing, let me also say more about the mean field theory. So the idea is that you do have some choice of this Tij, and the idea is different parameter space in the original spin Hamiltonian may require different choices of this this hopping parameter to describe it somewhat faithfully. And for reason, people understood, well, people don't actually completely understood, but for some reason, there exist some, some choices seem to be nicer than the others. Okay? And for this talk, the kind of examples I'll be talking about involve choices of this hopping parameter such that this free fermion problem at low energy, they basically give you a bunch of gapless Dirac fermions. Okay? So for example, on the triangle lattice, the choice of Tij is such that the flux seen by the fermions when they hop on the lattice is pi for all downward triangles and 0 flux for all the upward triangles.
And is so Tij means, diagonal in this alpha beta basis then? Or?
Yes, it is diagonal. Yeah, because I'm assuming spin rotation symmetry. So so alpha beta. Right. Yeah, it should really be Tij delta alpha beta. Mm-hmm. And sorry, by flux, let me clarify. It means that if I take the product of Tij on all the 3 bonds, the phase factor associated with that Tij is I define it to be the flux. Okay. So if I put in this kind of configuration and I just solve the band theory, you'll see that at low energy, what I end up having are 2 Dirac fermions for each spin. So I'll basically get 4 Dirac fermions. And here, let me also clarify. By 1 Dirac fermion, I mean a 2-component Dirac fermion. So I'm working in 2 + 1 dimension. There's some historical motivation for considering this type of mean field ansatz. It comes from old stories like the resonating valence bond theory and even some motivation from cuprates. But in modern times, with nowadays we understand reasonably well that this type of phases may or may not be there in cuprates. If you ask me to bet, I would probably say it's probably not there. But it may as well appear in some other materials, which I'll talk about later, a bit later. Okay. So bottom line is this type of mean field ansatz may be actually relevant for real systems. All right, so so here comes the question of what, if I try to go beyond the mean field theory a little bit, right? If I try to include some fluctuation, what are the most important fluctuating degrees of freedom that I should include? Right? So it turns out when I do this rewriting this spin operator into this fermion product, you realize that I'm doing something quite funny here. So first of all, you realize the dimension of the Hilbert space is enlarged, as pointed out very correctly before. So this S operator has, let's say if it's a spin half moment, it only has a two-dimensional Hilbert space. But if I have a spin half fermion here, then looks like I have a four-dimensional Hilbert space. So so if I want to represent the physics faithfully, I should project this this four-dimensional Hilbert space back to the original physical two-dimensional Hilbert space in some fashion. Okay? So if you just stare at this expression a little bit, you realize that the way to project that is basically to require that the total occupation number, the total fermion charge, is 1 on every site, right? Because if I have one fermion that's spin half, of course the Hilbert space is a two-dimensional Hilbert space, right? Whether I have the one fermion being spin up or spin down, that's it. And related to that is a gauge symmetry or gauge redundancy associated with this rewriting. If you stare at this rewriting, you realize that if I multiply the fermion operator F by an arbitrary U1 phase factor, then absolutely nothing will change. There's no change in physics associated with this rewriting. And this, so here, this is the local U1 rotation I can do. And this phase angle alpha can vary from site to site. And doesn't matter how it varies from site to site, absolutely nothing should change physically. Right? And that's almost the definition of a gauge redundancy.
Chong, I have a question, but at spin 1/2, you also have a particle hole symmetry, which you can then compound with the U1, so you get a SU2 then.
Yeah, yes. That's my star here.
Okay.
For experts, it turns out for the examples that I will be talking about, they don't matter because the mean field ansatz will be breaking that symmetry anyway. But if you work on, for example, square lattice and so on, that is actually a thing to be pay attention to.
But in general, when you rewrite the spins in terms of fermions, when you write it as a trace, right? If you do in the Nambu spinner representation, you can write it as a trace of psi dagger psi, right? And then then of course you generally see that there is a SU2 symmetry.
In general, yes, absolutely.
In general.
Yes, absolutely. So now let's just worry about the U1. For some reason, for this examples, let's not worry about SU2. So once I realize that there is this gauge redundancy, then if I think about fluctuation, including fluctuations on top of that mean field, the most important fluctuating degrees of freedom, it kind of becomes obvious that it should be fluctuating or dynamical gauge field, with the gauge symmetry being whatever gauge symmetry that's here. So in this case, it will be a U1 gauge dynamical gauge field that's coupled to the spin knots. Okay. And for U1 gauge symmetry, I can define the notion of gauge charge per site. So naively, since F goes to, gets multiplied by phase under the U1 symmetry is just generated by the total occupation number of the fermion. But here comes the -1, if you like, a background charge of -1 here. And that's simply saying that if I require gauge invariance on every site, then I should have the gauge charge being 0 on every site. But that translates to having a occupation number, or the total fermion charge, being exactly 1 on every site, right? Because as I mentioned, if I have 1 fermion per site, that naturally recovers my physical spin 1/2 Hilbert space. Okay. And the idea of doing mean field plus weak fluctuation is to say that let's include gauge fluctuation, but let's only demand that this charge, charge neutrality condition to be true on average. Right? So in the spirit of RG, the hope is that this relaxed requirement doesn't really hurt you if I'm mainly interested in the IR physics, long distance and low energy. Okay. So if I do that, remember previously I mentioned that I'm interested in mean field ansatz that will give you some Dirac fermions at low energy. So if you include gauge fluctuation this way, the continuum theory you will end up getting is exactly a QED3, specifically 4 flavors of Dirac fermions coupled to a dynamical U1 gauge field. Okay, so it's we'll just call it QED3 with NF equal to 4. So NF is the flavor number of the Dirac fermion.
Okay. Can I ask something, Chong?
Yes.
So here the gauge field will have 1 degree of freedom, right? And so you're adding still a degree of freedom to the system.
To some extent, adding a gauge field is like trying to subtract some degree of freedom, right?
Yes, but if that is propagating, it has its own degree of freedom, which is 1.
Yeah. Yeah. The idea is if it's strongly coupled, let's say if it's infinitely strongly coupled, even on the lattice, then you can imagine. Okay, sorry. If it's strongly coupled in the IR, what happens is that you enter into the confined phase, and then that's literally subtracting degree of freedom. The idea is that, well, since now it's formulated in terms of gauge theory, then depending on your coupling parameter, it may have the chance of entering deconfined region, in which case you do have gauge fields. They do behave like,
of course,
real degree.
Instead of F², if you have simply a Chern-Simons-like term, then of course you are not adding any degree of freedom, I guess. But
no, yeah, but here it's kind of important that I don't have the Chern-Simons.
Chern-Simons, you have this F², but you're saying that somehow the confinement helps you to, in the infrared, then it would have, these 2 theories would be indistinguishable in infrared, even though you have added a degree of freedom, then this would still be. But what I'm very confused about is, in what sense is this? Is it the mu is some sort of kind of a mean field that you are putting in? This plays a role of a mean field, this gauge field.
So, sorry. Maybe I probably didn't quite get it. Can you repeat the last statement again? The last sentence again?
Yeah, I'm saying that when you discretize this QED3, say on a lattice, should I think of this gauge field as some sort of a mean field?
No, the gauge field. Well, if you put it on the lattice, probably the most convenient way to think of the gauge field is that it's some field that's defined on the links of this lattice. Right? It's still dynamical, right? So they still fluctuate.
Dynamical. Okay.
Yeah.
Okay.
So it's really it's really a lattice gauge theory. Maybe with continuous time, that's probably better defined. But yeah.
Okay, thanks.
Sure.
So another question I have, if I may, when you mention dynamical U1 gauge field, are
Yes.
you simply referring to the fluctuations of the temporal component of the gauge field, which
No,
then
no, no.
implies
All
the one
components.
fermion
All
per side?
components.
So also the
All
spatial
components.
phase factor
Yes, yes.
fluctuations.
So
Right?
yeah.
Okay.
So okay, good point. Good point. In the so there is a standard derivation in the literature, which I didn't go into detail here, using path integral and so on to quote unquote derive this theory. So there you will see that the temporal fluctuation comes literally from imposing this constraint of 1 fermion per site, while the spatial fluctuation comes from decomposing decomposing the full theory, which is let's say, if I start from this theory S dot S and I rewrite the S operator this way, you see that it's a pretty badly looking 4 fermion coupling.
Right.
So,
Okay.
so
My
if I want
confusion
to do
simply
mean
arose.
field,
Yeah. Okay. Yeah, I got it. Yeah. Okay.
if I decompose it, it becomes the fluctuation of this Tij, the phase fluctuation of this Tij.
No, my confusion arose because you wrote the 1 fermion per side constraint, which, as you rightly mentioned, comes from the temporal fluctuation part. So I thought you're taking only that part into account.
No.
Okay.
It's the idea is once you impose this gauge constraint, essentially for consistency, if I start from a mean field, the only consistent fluctuation I can put in is a gauge field with all components. So you can view it from either way, right? You can start from the microscopics and try to derive it, or you can just start from the mean field and say on consistency ground, this is the only thing that makes sense.
Right.
So,
Yeah. Okay. Thanks.
Sure.
Yeah, Chong, I think one way to count the degrees of freedom, if you tell me if I'm doing it correctly, is that the gauge field, of course, adds a degree of freedom, but because you're looking at rho goes to 0, or so you're having only some overall charge fluctuation or something. So you don't see the patterns because you're looking into a singlet subspace, I guess. So
basically, yeah,
so
yes,
that probably,
yes. So
yeah.
So yes, on the lattice, that's quite literally what happens. Yeah. All right. So so again, now a few words about QED3. The thing is, this is a theory that's much weirder than real life QED, which is in 4 dimension. So unlike real life QED in 4 dimension, which is weakly coupled in the IR, in 3 dimension, this kind of gauge matter coupling flows to strong coupling. If I go to IR, so they are much more interesting. And strictly speaking, let's say at NF equal to 4, there's no analytical proof that the theory flows to a very interesting theory. For example, it could well be that the theory spontaneously breaks symmetry and open up a mass gap, essentially a spontaneous chiral symmetry breaking phase. So that's a priori possible. But here, let me assume a more interesting scenario, which is the theory actually flows to a critical state or a conformal field theory in the IR. So we know that for sufficiently large n, if I go to NF equal to, I don't know, 40 or something, this will definitely happen. So the theory is controlled in 1 over n expansion. Okay. So in fact, this scenario is supported by recent numerics from the Lattice Monte Carlo studies, at least when monopoles are ignored. So I'll come back to this later. But if this indeed happens, then already immediately there will be some interesting physical consequence. For example, one can show that there will be an emergent SU4 spin valley symmetry. So on the lattice scale, you have a twofold index from the spin and a twofold index from what we call value. So value really means the 2 different momentum points at which your Dirac fermions are located in momentum space. Right? They are different indices and there's no symmetry that relate them. But if the theory flows to a CFT, the prediction is that there will be an emergent SU4 flavor symmetry. Okay. Also, since I'm dealing with a U1 gauge field in 2+1 dimension, in 3 dimension, there is something special about U1 gauge theory in 3 dimension, which is the gauge flux is naturally a conserved current, just by Bianchi identity. Okay, so this I can define this gauge flux this way. What that implies is that there is a global U1 symmetry associated with the gauge flux. Sometimes people call it the U1, the topological U1 symmetry of QED in 3 dimension. Okay. So you get a lot of quite non-trivial set of emergent symmetries. And now let me talk about the real focus of this work, which is monopoles in QED3. So as I mentioned, there is a U1, there is a global U1 charge that's basically the flux of the U1 gauge field. Then the natural thing to talk about are operators that are actually charged under this global U1 flux symmetry. Okay. And these are the monopole operators. So by definition, then there are operators that inserts a 2π flux, let's say, into your space. So in this figure, imagine that this vertical axis being time, and you have your xy plane here, right? So so this is an operator that, think of it as a tunneling, right? At some point in time, the total flux in your spatial plane flips by amount of 2π. Okay. So that's you can always define such an operator whenever you have a U1 gauge theory, or in fact UN gauge theory in 2+1 dimension. But in QED3, if I have gapless Dirac fermions, there is something special here, which is each flavor of Dirac fermion will contribute a 0 mode whenever you have such a flux insertion. You can make this statement more precise with state operator correspondence, but let me not go into there.
May I ask a question, Chong? Sorry.
Yes.
Yes. My thing is that when you say that there's this emergent symmetry and there's a conserved charge, but that's only in the infrared limit, right? In the long wavelength limit, right? So of course you're allowed to do this insertion of 2π, additional charge by these operators, because this conservation is not present on the lattice scale, right? On the lattice scale, somehow you must. Right? I mean, am I understanding correctly? Otherwise, you won't be allowed to do it.
There are two separate issues here, actually. Yeah. So the first point is, yes, this symmetries, including the U1 flux conservation symmetry, strictly speaking, is there only in the IR. You can define a different version of the theory in which this will be even a symmetry even in the UV, but that you have to define a non-compact version of the gauge theory on the lattice and so on, which is different from what we care about here. Right, so the symmetry is only strictly there in the UV, but a different question is whether this operator is well defined or makes sense away from the UV. The answer is yes. So the idea is, even if the symmetry is not there, the operator can be there. Well, it's basically like saying, even if you don't have U1 symmetry, the boson creation annihilation operator may still be well defined. Right? They may or may not actually have expectation value, but at least they are defined. Right? Because you can talk about, essentially that's because even if this is not conserved, you can still ask how many charges you have, right?
But when the symmetry is present, will you be allowed to modify the charge via these operators?
Right. So a different question is, when these operators are well defined, can you add them to your Lagrangian, right? So there, the answer is, if the symmetry is strictly there, you're not allowed to add this monopole operator as perturbation to your Lagrangian just because there's a symmetry. But without assuming that exact symmetry, let's say the symmetry is just emergent, then a priori, you should be allowed to add these operators into your Lagrangian.
And that is the reason you're adding them.
Yes. Well, okay. Here I'm not yet adding them. I'm just examining the property of the operator.
Okay.
Right? So the idea is you first figure out what the property of the monopoles, especially under various global symmetries, and then you ask, are you allowed to add them just by symmetry?
Okay, great.
So that will be the rule of the game. Yeah.
Okay.
Sorry, Chong, I thought that you were saying that you're not really deforming the Lagrangian, but simply creating states by inserting these operators.
Yes. At this stage, I am just doing that.
Okay.
Yeah. I will talk about possibly deforming the Lagrangian with these funny operators later. But at this stage, I'm just asking the operator itself, what's the property, right? And of course, the operator is defined by its property under insertion into the path integral and so on. So
so the question is whether this operator is relevant or irrelevant. That's what.
Whether it's relevant or irrelevant, whether it's allowed to be added into the Lagrangian by symmetry and so on. So that's the question. Yeah. All right. So right. Let me continue. So there is the bare operator I call, which is literally just putting it, imagine inserting a 2 pi flux, but the question is the zero modes by definition they come with zero energy. So whether you fill them or not, they don't affect the energies. So a priori you can fill the energy zero energy modes, the zero modes in whatever way you like. Energy-wise, they'll all be more or less equal.
Is this consistent with the gauge constraint that you could do it because you already imposed this?
Great. So that's exactly the point. It turns out if I impose gauge invariance, if I want this monopole operator to be gauge invariant, I should fill exactly half of the zero modes.
Okay.
So there are in total 4 zero modes. So as I said, each one come from a Dirac fermion, a single flavor of Dirac fermion. So I should fill two out of the 4, right? And that gives me in total 6 different ways to fill the zero modes. So each gauge invariant monopole operator, I write it this way. So this bare monopole operator followed by filling 2 out of the 4 zero modes. Okay. So here I'm representing the zero mode schematically here. So right and left represent the 2 momentum associated with the Dirac fermions, and there's the spin up and spin down index here. Right? So this is an example of the zero mode filling pattern with both spin up zero modes filled in the 2 values, but you can fill it in other ways. So there are in total 6 different ways, 6 orthogonal ways to do that. So that gives you a 6-fold degenerate monopole operator. Now one realizes that if I look at the flavor symmetry SU4, if I mod that by Z2, it's actually just SO6, right? So SU4 is the spinor group of SO6. Sorry. And if you go through some algebra, you realize that this 6 monopoles exactly form a vector representation for this SO6 flavor rotation symmetry. Okay. So in some sense, this 6-fold degenerate monopoles, they form essentially what I call a fundamental order parameters in this theory. So you can show that any other local operators, local gauge invariant operators, you can write out of this QED3 you can represent it as some kind of combinations in the OPE sense of this 6 monopole operators. Okay. And if I further look at, ask how does it transform, physically on the lattice, I don't have the SU4. I have some smaller symmetry, like I have some SO3 spin rotation, and I have, maybe some other symmetry like discrete translation and rotation symmetry. If I look at, for example, the continuous SO3 magnetic spin rotation symmetry, then just by looking at how the zero modes transform, one can convince yourself that out of these 6 monopoles, 3 of them form spin singlets, while the other 3 form SO3 spin triplets. Right? For example, the example shown in this figure with the both spin up zero modes field in both valleys, in both momentum, that's one of the 3 spin triplet momentum. Right? This is a spin 1 object under the physical SO3. Right? So 3 of them are spin triplets.
Okay, so if I understand correctly, you're saying that monopoles, by virtue of being local operators, will transform always linearly and not projectively.
Exactly.
Okay.
Exactly.
Okay.
Yeah. All right. So so it turns out for spin rotation, like the SO3 spin rotation, that's all you need. You just look at the zero modes, and then you figure out that you have the 6 monopole splits into 3 triplets and 3 singlets. There's no additional subtlety here. Essentially because the group SO3 is constraining enough. The problem turns out to be much more subtle if I look at other things like discrete translation and rotation or time reversal symmetries, right? So essentially, the idea is that now let me write this monopole, this phi I. So I comes with runs from 1 to 6. Also, my monopole is a complex operator. Right? Remember, it's charged under this U1 flux symmetry. So in total, there's the SO6 symmetry and the charge U1, the flux U1 symmetry. And a priori, if I transform under a microscopic symmetry, some lattice translation and rotation, then in the IR, that should act as some, if there's a rotation, then you should come with a continuous rotation. But on top of that, it should also be implemented as something like this, right? So here, this OIJ is an SO6 rotation matrix, right? But the thing is, because the phi is also charged under the U1 flux, a priori, a microscopic symmetry can also act with a non-trivial phase factor here. Right? So this is the U1 flux phase factor. And the tricky question is what is this phase factor associated with this each symmetry? Right? So this OIJ part is relatively simple because essentially you figure this out by asking how the Dirac fermions, the zero modes, essentially transform under the microscopic symmetries. That's relatively easy, just like the spin SO3 case I showed you. But this U1 part is harder. Okay. So conceptually, you can generalize this problem. This is a much more general issue than just here specifically for lattice QED. The conceptual question is, suppose I start from some UV system, let's say some lattice system, and I have on the lattice scale and some exact UV symmetry, right? In our example, it's going to be some SO3 spin rotation and some lattice translation, rotation, reflection, maybe time reversal, right? So it's quite discrete. The question is, how does this embed into my eventual emergent IR symmetry in my IR field theory, right? So in my IR field theory, the symmetry enlarges to a rather large emergent symmetry group. Right? So here I have the flavor SU4, which, as I explained, becomes the SO6 symmetry, and then there's a U1 flux symmetry. Don't worry about the quotient Z2. Well, the quotient Z2 is really just saying any charge 1 operator here should carry a SO6 vector or some odd rank representation, which is just saying which is just the monopoles. Okay. I also have emergent CPT symmetry and Lorentz and so on. Okay.
Can I ask
so
something?
the more yes.
So this CPT, because it's a field theory, I guess that's why it comes about.
Yeah. Yeah, this theory does. I should have mentioned this. So in the IR, this theory does have emergent Lorentz symmetry. But the thing is, for this particular theory, because there's no Chen-Simons and so on, you do have C, P, and T separately. Yeah, that's what I mean by CPT. Sorry. Yeah.
Okay, thanks. But why should UV symmetry go to something that has T in it? Because it's anti-unitary, right? I mean, this is.
Yeah. Sorry. This GUV also include time reversal. I should have mentioned that.
Okay. Okay.
Yeah.
Thanks.
In fact, that's quite common in your lattice spin system, because it just takes S to minus S. All right. So yeah. So in general, if I have a UV system with an emergent some emergent IR theory with some IR symmetry, in general, this GUV one expect the GUV to act as some subgroup in this GIR. Right? That's what I mean by embedding. Okay. So the question is, how do you figure out that embedding? Right? So which subgroup of GIR does GUV act as? Okay. So this is as I said, you can imagine this is a quite general problem in principle. Anytime you have a UV system, let's say a lattice system, with where in the IR you have more symmetry, you do in principle you do need to worry about this issue. But for simple examples like, let's say, Ising model, or in general Wilson-Fisher theory or free fermion, this is not a difficult problem. In fact, this is almost trivial. It's so trivial that you don't even really think about it most of the time. Because let's say for Ising model, the way you work it out is to realize that, let's say you go from Ising model into the IR continuum theory, which is a 5-4 scalar theory. But there we know that the 5-4 scalar is really a coarse-grained version of the lattice Ising spin, right? So as long as I know how the lattice spin transforms under various symmetries, let's say it's odd under Ising Z2 and under lattice translation rotation, it does pretty boring things. You just change the coordinate, nothing else. So just from this coarse graining relation, you know how the phi, the IR scalar field phi will transform under various symmetries. So it follows automatically. Nothing weird there. However, this issue is in general much more subtle if your IR theory involves objects like the topological disorder operators. Right. So the Dirac monopole in QED3 is just one example of topological disorder operators in your IR field theory. Okay. Because this is tricky because in general, topological disorder operators are hard to directly write in terms of some coarse-grained lattice degree of freedom. At least it's usually not a priori obvious how to do that. So for the lattice QED3, this difficulty can be phrased more concretely by noticing that if I move the monopoles, it's essentially it's a flux creation operator, right? If I move the U1 flux around in the lattice, let's say if I try to translate it by some discrete unit, or if I try to do rotation and so on, essentially it sees the entire field Dirac C. Right? So for example, if I try to do lattice translation, the monopole is moving under a background of entire field Dirac C, and the momentum is defined as the Berry phase that the monopole accumulates as you move the monopoles along the lattice. Right? That's how you define momentum. But that Berry phase has non-trivial contribution from the entire field Dirac C. So yeah, somehow you need to calculate that that contribution, and that's the subtle part. Okay. So for simpler theories, for example some bosonic or scalar version of QED3 in quantum magnets, that's been worked out in late 80s and early 90s by this author, by Houdin and later by Reed and Suchdev. But in general, this question is it hasn't been clear exactly how to answer this question for more complicated examples like the fermion QED3. And but I should also say for this particular problem, there have been partial success in the past, and usually relying partly on numerical computation. So that's the problem that I'll be will be interested in. But before actually telling you the answer, the solution, and how we solve it, let me also tell you why we care about it. Right? Okay. So there's the conceptual reason, of course, as I already explained. This is a piece of necessary information to fully characterize the state. Right? This embedding from when we have a UV system and we have the IR field theory, it's not enough to just say I have this IR field theory and it has this emergent symmetry. It's also necessary to specify how does the UV symmetry gets realized in this IR theory. Right? So by definition, that's a necessary information. But more practically, it actually determines several things. So the first issue is that it determines whether the U1 Dirac spin liquid actually exists as a stable phase. Right? So so this is important because that's exactly related to the issue raised earlier. So this monopole operator is charged, it transforms non-trivially under the IR symmetry. Right? It's charged under the topological U1. It's also SO6 vector. But on the lattice scale, I don't have that gigantic symmetry. I have some pretty mild SO3 and some discrete symmetries. So if the monopole actually if there exists some monopoles that actually transforms trivially under those microscopic symmetries, then I should be able to add those monopoles as perturbations into my theory, even into my IR continuum Lagrangian. Right? But if the most and then the question is, are these perturbations relevant? Right? If they are irrelevant, then okay, nobody cares. Right? They won't do anything. It's fine. But if they are relevant, they tend to drive you away from the conformal phase. It's not completely clear what they drive you to, but the usual expectation is that they may lead to symmetry breaking instabilities, and eventually leads you to some just rather conventional symmetry breaking orders. Okay.
Sorry, can I get a clarification? So you said
yes.
that you need to know how the UV symmetries are embedded in the IR symmetries, and then you want to see if there are these operators that you can write down in the infrared theory, which are which transform trivially under the UV symmetries. Is that correct?
Yes.
Okay,
yes.
thanks. Okay, because you want to preserve. So you're saying that in general you can have deformations which can preserve UV symmetries, but not necessarily this IR. But can break these IR symmetries. Right. But then, of course, you want to know which of them are relevant. Okay.
Yes.
Thanks.
Yes. So the idea. So now for this NF equal to 4 QED3, we actually know the scaling dimension of this monopole operators reasonably well. So there have been some large N calculation by these authors, And more recently, there have been lattice Monte Carlo calculations by these authors, and they more or less, they basically agree. They agree quite well, in fact. So the consensus by now, I think, is that for NF equal to 4, the 2 pi monopole, the charge 1 monopole, has scaling dimension that's roughly 1, which is strongly relevant. Okay? So the error, the margin of error is probably something like 0.1 or 0.2. You know, it's almost non-negotiable that it's going to be relevant. And if you go to higher monopoles, let's say monopole operators inserting 4 pi or 6 pi operators, unsurprisingly, the scaling dimension grows. I think by now it's quite clear that 6 pi monopoles are clearly irrelevant, and 4 pi is probably close to marginality, so it's harder to tell. But 2 pi is definitely relevant. Okay? So if there is a symmetry allowed 2 pi monopole, then chances you probably are not going to have a stable U1 Dirac spin liquid. Okay? So that's the first issue. It's probably the most important issue, whether the Dirac spin liquid really exists in some sense. Also, oh, I had the numbers wrong here. Sorry. But the second thing is if the Dirac spin liquid exists, right? So even if let's say if all the monopoles are symmetry disallowed, right? They carry some non-trivial symmetry under quantum number under the UV symmetry. Well, there are still important operators in the critical phase in the CFT. Right? In fact, they are the lowest. They have, among all the local operators, they have the lowest scaling dimension. So they are kind of the most important ones. So their quantum number, in fact, will determine some measurable consequences. For example, in spectroscopy, for example, if you do neutron scattering, right, then you are measuring essentially the most important, the most relevant operators that carries, for example, SO3 triplet under spin rotation. Right? That's what neutron scattering does. So the crystal momentum of this of the most relevant SO3 triplet monopole will determine which point in momentum space your neutron scattering will react to. Right? That will show up in actual experiments. So that's important. In fact, that will be a helpful signal for practical experimental detection of this U1 spin liquid. And another thing is that if I actively try to destroy the U1 spin liquid, let's say by tuning some microscopic parameter and get some access some phase transition and get a more conventional symmetry breaking order, the quantum numbers, the symmetry quantum numbers of the monopoles actually determine the nature of the symmetry breaking orders. Right? For example, what type of magnetic order do you get? What type of valence bond solid do you get, and so on? Because again, the monopoles are the natural order parameters, so their symmetry quantum number naturally determines that. Okay, so those are the reasons to care about the quantum numbers of these the monopoles. Okay, all right, so that's yeah, that's, oh, am I already out of the time?
Well, I mean, you can certainly, because we had many questions, so clearly we can take more time, no problem.
That was,
so
yeah, it's funny because that was the motivation part, but I'll speed up. Well, it's fine. I think the probably the most important thing is to convey that this is an interesting problem. But here's the summary of result in case you have to leave early and so on. The summary of result is that of course you can ask all those questions just from a pure lattice gauge theory point of view. Just put QED3 on the lattice and you can ask all those questions. So it turns out the answer depends on which lattice you are working on. Of course, it depends on the specific type of mean field ansatz, right? On each, even for a even for a given lattice, there may be multiple ways, to get this Dirac fermions. But here I'm referring to the kind of the simplest mean field ansatz, or the band structure that will give you this Dirac fermions at low energy. And and for those simple band structures, this is the result. The statement is that whether you have symmetry allowed monopoles or not in your QED3 or in your Dirac spin liquid, very much depend on what lattice you're working on. Right? It turns out for non-bipartite lattices like the triangular or Kagame lattice, the answer is that all the monopoles, or at least all the 2-pi monopoles, the most relevant ones, are forbidden by some microscopic symmetry. It could be SO3 spin rotation, or it could be the lattice translation and rotation symmetry. Okay? So there's no symmetry trivial monopole, and the theory may well be a stable critical phase. Turns out for on bipartite lattice, like square lattice or honeycomb lattice, there exists a trivial monopole, and which means you can add that to your theory, and the expectation is that it will eventually destabilize the QED3 and drive you to something else. That something else from other field theory consideration may well be something called the deconfined criticality. So it describes a transition between the nail and so this is what we call a valence bond solid phase. So this is a phase where you don't break, unlike the nail state, you don't break spin rotation symmetry. So each ellipse here represent a spin singlet, up, down, minus, down, up. So it's a spin singlet wave function. But as you can see from this figure, you break the lattice symmetry. You break, for example, this figure breaks some 90-degree rotation symmetry of the lattice. Okay. There is a good reason to expect this type of behavior on any bipartite lattice. It has to do with actually the hidden SU2 gauge symmetry that was mentioned earlier this talk. But let me not go into details of that. Okay. So the story on non-bipartite lattice is more interesting. So you do have the critical stable critical spin liquid phase, and if you move away from the spin liquid phase, let's say you crank up some other coupling strength and leads to some instability. These are the natural symmetry breaking orders you get. Again, the pattern is determined again by the quantum number of the monopole operators. And the most one neat or very consistent result is that, for example, on the triangle or Kagame lattice, if I move to a magnetically ordered phase from the Dirac spin liquid, the natural magnetic order I get is this famous 120-degree order. So this is the order that's most commonly seen on spin systems defined on this lattice. For example, if I take the triangle lattice, if I literally have just the nearest neighbor antiferromagnetic Heisenberg coupling, so just S.S for nearest neighbor, then this is the order that I'll be having. So that's known from numerics, for example.
Sorry, how does the monopole operator give this order? I didn't follow that. Sorry.
Yeah, that's what I'm going to explain next. So this is just a summary of how things behave. Okay, so yeah, that's exactly the thing I'm going to explain now. So the idea is, let's say you go to you start from the Dirac spin liquid, and now you make your life simpler. Right? Let's make our life simpler. The QED3 is some strongly coupled conformal field theory. It's hard to work with, but if I deform the theory, let's say with a mass term of this type, So this sigma is a Pauli matrix that acts on the, let's say, spin flavor index, right? So this is a chiral symmetry breaking mass term. In condensed matter literature, this is known as a quantum spin Hall mass. So if I add this mass term, then the Dirac fermions are now gapped, right? So the spin up fermions gets a negative mass, and the spin down fermions gets a positive mass. So this breaks, but it breaks spin rotation because it's sigma z. This is a vector under SO3 spin rotation, but it doesn't break any lattice symmetry. So that's just a fact that you can just check explicitly. It's just some algebra. And what's simplifying here is that if I now look at the monopoles, I no longer have the 6 degenerate monopoles, right? Because this term also picks out a favored monopoles out of the 6 monopoles. And it's kind of easy to see what happens here. So this term basically says that all spin up 0 modes now have a negative energy, while spin down 0 modes have a positive energy. That's what this term tells you on the 0 modes. So the 0 modes are no longer 0 modes; they are lifted, and the ground state correspond to filling up all the negative energy, well, quote unquote 0 modes, which is now just filling the spin up modes for both momentum. Okay. So this, but if you look at the remaining symmetry here, so this term, this mass quantum spin Hall mass term, it breaks the spin rotation SO3, but not completely, right? It leaves behind an SO2 rotation symmetry, which is just the rotation around the z-axis, right? It's just generated by sigma z. It commutes with that. So now if I look at the property of this monopole operator under that remaining SO2 spin rotation symmetry generated just by sigma z, you realize that it carries charge 1 under the sigma z spin rotation symmetry. Right? So charge 1 under sigma z rotation is basically Sx plus Isy. That is the spin raising or lowering operator. Right. So the idea is if I go to if I turn on a quantum spin Hall mass, then the fermions are gapped, and I have a Maxwell U1 gauge theory left in IR. And in the Maxwell U1 gauge theory, there is the monopole operator, which transforms like an Sx plus Isy, and this operator condenses to give me a symmetry breaking order. Right. And when the operator behaves like Sx plus Isy, we know that in magnetism, that basically tells you that it's a non-collinear magnetic order. It will behave somewhat like this, right? Because if you look at the patterns, sorry, let me explain that a little bit more carefully. The idea is if an operator like Sx plus Isy condenses, then you ask what's the remaining spin rotation symmetry? The answer is the spin rotation symmetry. The SO3 is now completely broken. Right? Just by the mass term like sigma z, it breaks the spin rotation to SO2. But this Sx plus Sy will further break the spin rotation symmetry to nothing. Okay? That's what we mean by non-collinear magnetic order. Okay? So a figure like this does satisfy that criteria. Right? For example, if you look at this figure, you realize that no matter what kind of spin rotation you do, this figure is not left invariant.
But is it obvious it should be 120 degree, or I don't know?
Exactly, that's the next question, right? Because even that can be satisfied by multiple ways of doing this, arranging this thing, and whether you get exactly the 120 degree order depends on exactly how this monopole operator transforms under lattice symmetries. And remember, this mass term transforms trivially under the lattice symmetry. So lattice symmetry breaking has nothing to do with the mass term. but the monopole operator may transform non-trivially under lattice symmetries. In fact, the lattice momentum of this monopole operator will decide what pattern of magnetic order you'll end up getting.
So
the question
can I
is,
understand part of your logic? So initially you put some term that destroys a part of the UV symmetry, right? That's what you do.
Yes.
You put some quantums, and then you ask what kind of monopole operators now you're allowed to add, and then this will further break this.
Oh,
but how do you know that
no,
this will?
Yeah, okay. Sorry. Yeah, I should have clarified this. Yeah, I forgot to mention this. So one crucial statement that I need to use is that if I have a free Maxwell theory, the monopole operator in the free Maxwell theory spontaneously condenses. Right. So essentially, a free Maxwell theory in 2 + 1 dimension is equivalent to a superfluid, in which the monopole operator is the order parameter that actually gets condensed. So you can think of the photon in 3 + 1 as the ghost modes of the monopole condensation.
Okay.
Yeah. So now the idea is this monopole operator, you don't have to add it by hand. It will condense anyway, spontaneously. That's the property of Maxwell theory in 2 + 1 dimension. For example, if you calculate the monopole correlation function, it's gonna have long range order. And that's a statement specifically true just for Maxwell theory. Right? If you have conformal field theory like QED3, that's not true.
So you're not considering NF is equal to 4 now?
Right, because I have the mass term, so the Dirac fermions are gapped. So I integrate out the Dirac fermions. I go to the energy scale below the gap.
Okay, I see now. Okay, this is what confused me. Okay, I understand.
Yeah, sorry. I think there's probably a missing slide or something.
So basically, you are not. This is disconnected from what you were saying earlier. So it's not the conformal field theory anymore.
Yeah, exactly. So the idea is that the story is way simpler once I add this mass term. Yeah.
Okay, thanks. Now it.
Yeah. So now the question is, what symmetry breaking order do I get? That's decided by the quantum number of this monopole operator. And of course, this will eventually be connected back to the QED3 because the symmetry quantum number of this monopole operator, essentially also comes from the symmetry quantum number of the monopoles in the QED3. Right. So this monopole is one of the 6 fundamental monopoles in the QED3. So if I solve this problem, I also solve the problem for QED3. That's the idea. Okay, so how do I decide the lattice symmetries of this object? Well, it turns out on the lattice there is a trick you can do, which is now I'm dealing with an insulating state at least from the fermion point of view. Right, the fermions are gapped, so they're just some insulators on the lattice. So what's the most simplest kind of insulator on the lattice you can imagine? Well, they are sometimes called the atomic insulator. That's the some says high school version of what an insulator is, right? An insulator is where a state where the charges just localized on some real space point and they don't move, right? And that's what you call a insulator. In quantum mechanical jargon, that's a product state or an atomic insulator. So the idea is that, well, let's deform, without breaking any symmetry, let's deform this insulator, this quantum spin Hall insulator, into an atomic limit. Okay. And then in the atomic limit, since I just have some localized charges sitting trivially at some real space point, it's much easier to ask what kind of Berry phase the monopole accumulates as it moves on the lattice. Right? So let me show you an example here, which actually happens to be so this is an example for the quantum spin Hall insulator. So remember the fermions are now gapped. It turns out I can deform the fermions into a limit where the gauge charges. So we're effectively as if I have one fermion sitting on every lattice site, and one fermion sitting on every one charge sitting on every center of the upward triangle, and -1 charge on every downward triangle. You may wonder what does negative charge means, since I'm just deforming fermion. I'll explain that later. But for now, just take my words. You have some effectively -1 gauge charge at the downward triangle center. Okay. The idea is if I only care about some discrete quantum number, for example, if I care about the angular momentum under a C3, under a 2 pi over 3 lattice rotation, right? Then the answer is going to be discrete. Right? It's going to be some power of e to the 2 pi I over 3. So if it's discrete, then as long as this deformation is continuous, doesn't break any symmetry, and doesn't close the gap, then the answer won't change. So I am free to deform the insulator into a atomic limit like this. Right? Of course, the non-trivial statement is that such a limit always exists, up to some subtlety, which let me not go into in detail here. That's basically true. You can deform an insulator on a lattice into this type of product state, this atomic limit. So once you have an atomic insulator like this, then you can figure out the lattice quantum number quite straightforwardly. The idea is that, for example, let's say if I ask a question, how does the monopole transform under a C3 rotation symmetry, a 2 pi over 3 rotation symmetry, let's say around this point, this center of the upward triangle, right? So imagine let's say putting some 2 pi flux here and do rotation, right? So the angular momentum is basically decided by the Aharonov-Bohm phase factor when I move a flux around a charge, or a charge around the flux, doesn't matter, right? So the angular momentum is then going to be basically given by the product of E and M, where M is the charge of the flux, right? So in this case, it's 1. If I talk about a 2 pi flux, and E is the charge that's localized at the center of that C3 rotation. Right? It's literally just the Aharonov-Bohm phase factor. So if I have charge 1 here, it means that if I do the C3 rotation 3 times, I get a phase factor of 2 pi, which means if I just do it 1 time, I get a phase factor of 2 pi over 3. So that gives me the angular momentum, the C3 angular momentum of my monopole around the upward triangle. And likewise, for downward triangle, I have -1 here, so then I'll get a phase factor of -2 pi over 3. And now it turns out that's enough to give me my momentum, because if you look at these two transformations, if you combine them in this way, right? Let's say I do a downward 2 pi over 3 rotation, and then followed by an upward -2 pi over 3 rotation. So if you look at how the spatial coordinates changes, that's equivalent to doing a translation in the x direction by 1 unit. Okay. So if I just combine the phase factor, I conclude that under a translation by 1 unit, I get a phase factor of 2 pi over 3. Okay. So basically, just by looking at how the charges are distributed, effectively distributed within the on the lattice, you can figure out how the monopoles transform. And now we've seen that the monopoles gets a phase factor of 2 pi over 3 under translation. But remember, this monopole is like a S plus. It's like Sx plus Sy. So it means that under a translation, the in-plane magnetic moment, Sx plus Isy, should rotate by a phase factor 2 pi over 3. that's basically just saying that your magnetic moment should rotate within the xy plane by 2 pi over 3, and that's exactly what this 120-degree order is doing on the lattice. So that's how one figures out that this quantum spin Hall insulator coupled to a U1 gauge field actually gives you the familiar 120-degree order. Right?
So is this a proof of some sort that this is something, this will be the phase of this theory or of this lattice that is effectively a proof, right?
for at least for this quantum spin Hall insulator, this is this is basically a derivation of the corresponding magnetic order. Yeah. Actually, let me skip this part. It turns out this lattice momentum of monopole is related to a very simple concept called known as the electric polarization of a crystalline insulator. It actually gives a somewhat more satisfactory definition, in some sense, of electric polarizations compared to the standard definition. But let me not get into detail of that because I think I'm out of time already. Okay, this is also some technical thing which I don't want to get into. But the thing is, I should explain a little bit. How do you get a pattern like this, starting from a gapped insulator on the lattice? So let me just say that there is a well-established calculational recipe developed within the topological band theory over the past several years. So essentially, you give me some lattice Hamiltonian, and I can calculate a pattern like this for you, just from information of the Bloch wave function in band theory. Okay.
So you're saying that there is a way to where you can factorize the wave function always. There is a way to deform it. And
yeah.
Okay. Yes.
Yeah. So there is a well-established calculational recipe here, right? But one thing that's worth explaining is what is this negative one here, right? Because I'm just deforming a bunch of occupied fermions, and how do I get negative charges? The idea is that I lied a little bit by saying that you can always deform the insulator to a trivial product state like this. It turns out in this case you cannot, but you can if you add some trivial product state to the system, and the total system, right? So your original insulator added with some trivial atomic insulator can together they can deform into another trivial atomic insulator. So this auxiliary insulator you had to add essentially from the original insulator point of view behaves like a canceling of some negative charges. So this is a concept called the fragile topology. Let me accelerate. You can check this calculation or also numerically, and there's some way to do it. It works out basically. Okay. Let me finally say something about the consequence, which is on the triangle lattice, for example. Now you have a stable Dirac. You can upgrade this calculation to the full 6-fold monopoles for the Dirac spin liquid phase. Now the critical phase. Turns out to be not that complicated. And the conclusion is that for triangle lattice or Kagame, all the monopoles are trivial in one way or another. Right? They may be trivial under translation. They may be non-trivial under translation or rotation or spin rotation, but one way or another, they will be non-trivial. So the Dirac spin liquid is stable, and the monopoles are still important critical degrees of fluctuation. They are the local operators, And one consequence is that you have non-trivial spectral weight at this special momentums. For example, I've shown you that the spin triplet, what I've shown you in the previous example is that the spin triplet monopole operators on the triangle lattice Dirac spin liquid will carry momentum 2 pi over 3. And in the lattice Brownian zone, that in the standard representation, they correspond to the corners of the Brownian zone. So the prediction is that if I do neutron scattering, or if I calculate the spin-spin correlation function, the spectral weight will accumulate around the Brownian zone corner. That's something people can check explicitly, and it has been checked, numerically observed. For example, on the triangular J1, J2 spin 1/2 model, which I think a lot of us believe that realizes this Dirac spin liquid. Think J1, J2 means you have the nearest neighbor and next neighbor antiferromagnetic coupling. I think the Dirac spin liquid is realized around J2 over J1 around about 0.1. And to a less certain degree, it's probably also been experimentally seen under neutron scattering in this particular material. But again, that's less certain. It comes with much more uncertainty. And with that, let me just stop here. And this is the summary slide, which you can read. The funny thing that the entertaining thing for me is that somehow this old concept in band topology. Band topology sounds fancy. It looks like something modern, but if you think about things like the atomic limit, people usually call it 1 near center, and that's almost 100-year-old concept. And then there's another very old, very subject with long history in condensed matter physics, which is competing magnetic orders and so on. So these two subjects gets connected through the tool, through this funny objects of monopoles in QED3. And with that, let me just stop here and thank you for your patience, and sorry for going over time.
Thank you, Chong. It was really a very nice talk. We learned a lot.
Thanks.
Thanks for the great talk. So time for questions, please.
So you considered monopoles in the vector representation, right, of SO6?
Yes. Yes.
Are you also thinking of considering monopoles which transform under more higher dimensional representations?
Yes. So you can definitely do that. I think the only constraint here is that, well, because of that mod Z2 constraint, if it's 2 pi monopole, it has to transform under some odd rank of SO6. So the thing is, if you go to higher rank, the monopoles gain dimension become larger, so they become less relevant. For example, you can think about, let's say, rank 3 operator of monopoles. I think that's already irrelevant. Well, actually, no. Okay, that's close to marginality. We don't know exactly if it's relevant or not. Within large N, it's close to marginality.
Okay, and my second sort of question is that we know from this projective symmetry group classification of quantum spin liquids that Xiaogang Wen, introduced, that we can also have what I call as U1 gapless chiral spin liquid. So so the standard Kalmar-Laughlin type states are usually gapped. They break inversion, symmetry, and time reversal. But you can also have gapless chiral. So any statement about the stability of U1 gapless chiral spin liquids on the triangular lattice, as has been classified in a paper by Samuel Beery, Laura Messio, and Claire Lullier. I mean, are these stable phases? I mean, or
actually, okay, I haven't thought about that. Okay, I need to understand exactly what's the field content of that. So are they some QED3 with Chen-Simon term? That's my vague impression, or
Well, I mean, that's a good point. Their field theory has actually not been explored. I mean, all we know is that at low energy, the invariant gauge group of the mean field ansatz is U1.
Right.
And of course, I mean, they could have a Dirac dispersion, or they could have a spin-on Fermi surface,
I see.
Uh,
Okay.
but beyond that, actually, we don't know. I mean, in a sense, I mean, the mean field, we know the TIJs, and what are the flux patterns they give rise to. And there are, of course, some non-trivial fluxes which are not 0 or pi, which break time reversal symmetry.
But you said these things break time reversal symmetry.
Yeah, because in the PSG classification, you don't impose time reversal. So in that sense, while classifying, you only impose spin rotation and certain lattice symmetries, but you would, for example, not impose inversion and time reversal.
I see. I see. I think. Okay.
But you have
think to have
gapless
such
points. Yeah.
But correct me if I'm wrong. The gapless points are probably all they probably have just Fermi surface, right? Can you have Dirac fermion that's stable there?
Possibly not. I mean, the ones that I have sort of come across that were numerically investigated all had a Fermi surface.
Yeah, that's probably the more natural expectation. Yeah, I think for U1 coupled to Fermi surface, at least these monopoles are they're not a serious issue there because they turn to be strongly suppressed.
Okay.
It's only for conformal theories that you have to seriously worry about these monopoles.
I see. Okay.
Yeah, basically you think of Fermi surface as having infinitely many fermions. So
right.
Yeah.
Okay. I have a related question, I think. So some of this symmetries could be anomalous, right? If you have a chiral.
Yes.
And how does it play a role in the story?
Oh yeah, there's a very very interesting story there. So yes, so if you look at the full IR symmetry, there is a 't-Hooft anomaly here. Actually, the 't-Hooft anomaly takes a somewhat complicated form. What happens is that if you focus on if you restrict that IR symmetry to the UV symmetry, then then it turns out the 't-Hooft anomaly, when you restrict it to the UV symmetry, becomes basically what's known as the Lipschitz-Lattice theorem on the lattice. For example, what you will see is that effectively there is a mutual anomaly between spin rotation symmetry and, for example, lattice translation symmetry. There's a mutual anomaly there, and that's basically reflecting the famous statement that if I have spin 1/2 moment per unit cell, then the IR theory cannot be too trivial. And so over the past several years, we realized that this celebrated statement that dates back to the 60s by Lipschitz-Lattice actually has an interpretation in terms of 't-Hooft anomaly. Yeah, so it's a non-trivial match there. There's an entire set of stories behind.
Okay, so I had my last question is that, I mean, if you generalize this to spin S Dirac spin liquids with some generalized gauge group like U2S.
Yeah.
Yeah. Oh, okay.
Yeah. So the natural generalization is to U2S QCD.
And what about the stability on bipartite and non-bipartite? Does that remain the same? I mean, the same here. Did there exist a trivial monopole on the bipartite?
Yes.
Okay.
It turns out, I think what happened is because that parton decomposition comes with a SP2S
SP2,
symmetry, gauge symmetry, and so basically the reasoning all go through for so there's nothing from if you just look at kinematics, right, then there's nothing too special about spin 1/2. You just generalize as quite straightforward.
You lose particle hole symmetry, right? And spin 1 and higher. So at the half filling, you don't need.
You actually do have particle hole symmetry. The SP2S contains a particle hole part.
Okay. Do you expect that the spin liquid of like J1,
that
J2 on
breaks
the
the particle
triangular?
bond.
So do you expect the J1, J2 spin liquid around 0.1 to survive for higher spin? I mean,
No,
or
yeah,
is it
that's
just
that. Yeah, yeah. So that's why I say if you look at kinematics, there's not much difference. But if you ask about dynamics, right? You ask whether this U, for example, U2 or U3 QCD3 with 4 flavors of Dirac fermion do exist as CFT in the IR. That's a very different question. The short answer is we don't know. You have, I don't think any theorists will be able to answer that question. You have to seriously do lattice numerics to decide that. So right now we don't know. Right? We know there will be a critical S above which you're not expected to have this. We don't know what's the critical S here. It may well be just above 1/2. We don't know. What we do know is that if you do this, if it's unstable, then from the monopole symmetry quantum number argument I mentioned, that the instability is most likely towards the natural 120-degree order. So that kind of matches nicely with the
suppose it turns out that the spin liquid regime of the J1, J2 triangular shrinks but still remains finite for spin 1. Then this theory of yours for U2S would come into picture, right?
Yes, you'll get a U2 QCD. Yeah, that would be an extremely cool scenario, right?
Then I should do
yeah. So in fact, there was some experiment on some spin 3/2 system that appeared to have shown some interesting signature, which was basically the motivation of this paper we wrote. But it turns out that experiment eventually turned out to be less interesting than what we originally anticipated. So right now we actually don't know whether spin 1 or spin 3/2 will have stable Dirac spin liquid.
So is there some like there's no DMRG evidence for that, like spin 1, J1, J2 triangle?
I think there's no DMRG study on any spin 3/2 system, just because it's a costly system.
Right.
Spin 1, I think I don't see any documented results. I've heard rumors from various people that they haven't seen anything. But we know looking for critical spin liquids in DMRG is kind of a tricky business anyway.
Right, indeed.
So right now we don't know. Yeah. So but that remains as a pretty cool possibility.
So that's something interesting to always look for. Yeah. Okay, great. That's all from my side. Thanks so much for this wonderful talk and wonderful interaction session.
Thanks for having me around. It's been fun.
It's a pleasure.
Okay, so I guess it has been already very late, and hopefully, Chong, you can come back and give us a talk on your work on fractons and all this recently, which I've seen on the archive. So we should have you once more at least. And hopefully you will also visit us in Chennai.
We should invite you for a physical visit, a real visit.
Yeah, hopefully we'll be able to have that within some finite time. Hopefully.
Finite time, yes, that's important.
Okay. On this note, then have a good day, Chong, and
thanks,
good night.
Thanks,
thank you.
Good night.
Bye-bye.
Good night.
All right.
Good night. Bye-bye.
Bye.
Okay. Bye.